Everything you have ever touched is made from something that, by all rights, should not exist. Every atom in your body, every star in the night sky, every planet, every galaxy, every living thing. According to our best understanding of physics, the universe should have destroyed itself almost as soon as it began. In the first moments after the Big Bang, matter and antimatter were created together in almost perfect balance. Whenever the two meet, they annihilate one another completely, leaving behind nothing but light. The early universe should have been the scene of total destruction, and almost was. For every billion particles of antimatter, there were 1 billion and 1 particles of matter, just one extra particle, one survivor in every billion. That unimaginably small imbalance became every galaxy, every star, every planet, and every person who has ever lived. No one knows why it happened. The mystery does not end there. The laws of physics depend on a handful of fundamental numbers that appear to have no deeper explanation. Change even one of them by the tiniest amount, and stars never ignite, atoms never form, and the universe remains dark and empty forever. Then there is empty space itself. According to modern physics, the energy of the vacuum should be larger by a factor of 10 to the power of 120, the greatest disagreement between theory and observation in the history of science. If those calculations were correct, the universe would have expanded so violently that matter could never have gathered into anything at all. The deeper physicists have looked into the origin of reality, the stranger the existence of reality itself has become. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. The story begins with a question so simple that modern physics still cannot answer it. Why is there something instead of nothing? Close your eyes for a moment and picture an empty place. Most of us imagine darkness stretching forever, an endless black backdrop waiting for something to appear. Yet even that picture contains a stage. It contains distance, direction, and space itself. The mind struggles to imagine anything less. We naturally replace nothing with emptiness, even though emptiness is already something. Physics asks us to go further. True physical nothing contains no space waiting to expand. It contains no passage of time, no energy, no particles, no quantum fields, no dimensions, and no physical laws to govern events. There is no place where anything could happen. There is no clock marking one instant after another. There is simply no framework within which existence could even begin. But this creates an astonishing puzzle. If the universe emerged from such an absence, what could that statement truly mean? Our language depends upon time. Every explanation begins with words such as before, after, cause, and consequence. Those ideas lose their meaning if time itself has not yet appeared. Modern cosmology suggests exactly that. According to our best current understanding, time began together with the universe. Asking what happened before the beginning may resemble asking what lies farther north than the North Pole. The question itself may point beyond the limits of meaningful description. The event we call the Big Bang is often imagined as an explosion bursting into an empty cosmos. The picture feels familiar, yet it is deeply misleading. Space was not expanding into a larger container. Space itself expanded from an unimaginably hot and dense beginning. Every region of today's observable universe shared that common origin as expansion unfolded everywhere at once. At the earliest instant we can describe, physicists encounter what is called a singularity. A singularity marks the place where our mathematical descriptions cease to give reliable answers. The theory of general relativity predicts one outcome, while quantum mechanics predicts another. Both theories succeed with remarkable precision in their own domains, yet together they refuse to produce a complete account of the beginning. We measure the universe to be about 13.8 billion years old through observations of the cosmic microwave background, the ancient glow left behind after the earliest stages of expansion. That faint radiation still fills every direction of the sky, carrying a record from an era when the cosmos first became transparent to light. But every answer uncovered by that ancient light reveals another unanswered condition beneath it. Why did space expand at all? Why did the laws of nature possess exactly the form they do? Why were the starting conditions balanced with such astonishing precision? As we continue this journey together, you begin to see that the greatest mystery may never have been how the universe evolved. It may be why reality found a way to exist in the first place. Imagine compressing every future galaxy, every future ocean, and every future living cell into less than the span of a single heartbeat. That almost impossible interval carried the fate of everything we would eventually come to know. During the universe's first second, the foundations of existence were established with astonishing precision. A slight difference in those opening moments would have left nothing familiar behind. We begin at the earliest interval that modern physics can meaningfully describe, known as Planck time. This unimaginably brief moment lasted about 1/10 million trillion trillion trillionth of a second. At that stage, the four fundamental forces of nature were united into what physicists believe was a single superforce: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force behaved as one. The separate rules governing the universe today had not yet emerged, but the unity did not last. As the universe expanded and cooled, gravity became the first force to separate from the others. That separation transformed reality. Structure became possible. Distinctions began to appear where none had existed before, allowing the young cosmos to follow a path toward increasing complexity rather than remaining a perfectly featureless state. Within another unimaginably brief interval, cosmic inflation began. Inflation describes an episode of extraordinarily rapid expansion during which space itself grew faster than light could travel through it. This did not violate the familiar speed limit of light because space was stretching rather than objects moving across space. During this expansion, the universe doubled in size at least 90 times before inflation abruptly ended. That astonishing growth accomplished something essential. Tiny irregularities already present within the infant universe were stretched across enormous distances while remaining remarkably uniform overall. Measurements of the cosmic microwave background reveal variations of only about 1 part in 100,000. Those slight differences later became the gravitational seeds from which galaxies eventually formed. But expansion alone could not create matter. As cooling continued, the universe reached conditions allowing quarks, the fundamental particles that combine to form protons and neutrons, to bind together. This happened after about 1 millionth of a second. Stable building blocks of ordinary matter could finally begin to emerge from the earlier sea of energetic particles. By the time the first full second arrived, another important transition unfolded. Neutrinos, almost massless particles that rarely interact with anything, stopped exchanging energy with surrounding matter and streamed freely across the expanding universe. Even now, roughly 330 neutrinos pass through every cubic centimeter around you at every moment, almost never leaving a trace of their passage. Less than 3 minutes after the beginning, the essential architecture of matter already existed. Every future star, planet, mountain, and living creature depended upon what endured during those opening moments. We often imagine history unfolding across billions of years, But the deepest foundations of that history were established almost immediately. Among every narrow escape woven into cosmic history, one stands apart for both its precision and its consequences. We can trace it through experiments, particle accelerators, and mathematical predictions. Yet, despite decades of investigation, its deepest cause remains hidden. Every object you have ever known depends upon an imbalance so slight that it almost vanished before the universe had time to grow. According to the standard model of particle physics, the most thoroughly tested framework describing fundamental particles and their interactions, the beginning should have created matter and antimatter in exactly equal amounts. Antimatter resembles ordinary matter almost perfectly, except its electric charge is reversed. Whenever a particle meets its antimatter partner, both disappear in a burst of pure light. Their mass becomes energy, leaving no solid material behind. That prediction leads to a startling conclusion. If the newborn universe truly contained perfect balance, every particle would have found its opposite. The result would have been complete annihilation. Light would have flooded the expanding cosmos, but no atoms, planets, or living creatures would ever have emerged from that brilliant aftermath. But nature followed a slightly different path. Observations reveal what physicists call baryon asymmetry, meaning ordinary matter gained the smallest imaginable advantage. For roughly every 1 billion antimatter particles, there existed 1 billion and 1 particles of matter. After almost every encounter ended in mutual destruction, that single surviving particle remained. Those rare survivors eventually became every atom found within every galaxy we observe today. The process responsible for creating this imbalance is known as baryogenesis. The name simply means the origin of ordinary matter. Scientists are confident that baryogenesis occurred because its results surround us everywhere. But confidence about the outcome has never become certainty about the mechanism. The crucial event itself remains hidden behind the earliest moments of cosmic history. In 1967, the Soviet physicist Andrei Sakharov identified 3 essential requirements that baryogenesis must satisfy. These ideas, now called the Sakharov conditions, describe the circumstances needed for matter to gain its tiny advantage over antimatter. Each condition fits naturally within modern physics. Yet, current theories still fail to explain how all 3 combined strongly enough to produce the imbalance we measure today. But researchers have uncovered one important clue. Experiments reveal a phenomenon called charge parity violation, a subtle difference in how certain matter particles and antimatter particles behave during specific interactions. In plain language, nature treats the two almost, but not completely, alike. That discovery demonstrated that perfect symmetry does not always hold. Unfortunately, the observed amount of charge parity violation falls far short of explaining the enormous survival of matter across the universe. Something else must have contributed during those first fleeting moments. Whatever produced that additional imbalance has not yet been identified. We know it happened because you, every star above us, and every world beyond our own are living evidence that one extra particle endured when almost everything else disappeared. Imagine opening a vast instruction book that contains no explanations, only answers. Every page lists a value with astonishing precision, yet nowhere does it tell you why those values were chosen. That is remarkably close to the situation facing modern physics. Beneath every star, every atom, and every beam of light lies a collection of fundamental constants whose values appear fixed, exact, and deeply mysterious. Current physics relies on about 26 dimensionless constants. Dimensionless simply means they have no physical units attached to them. They are pure numbers. They do not measure length, time, or mass. Instead, they determine how the laws of nature behave. Scientists can measure these constants with extraordinary accuracy, yet no accepted theory derives them from anything deeper. One of the most famous is the fine structure constant. This number governs the strength of electromagnetic interactions, shaping how light interacts with electrically charged particles. It has been measured to roughly 11 decimal places with astonishing consistency. If its value had been only about 4% larger, the nuclear reactions inside stars would have failed to produce enough carbon. Without carbon, the chemistry required for living organisms would never have emerged. But the fine structure constant is only one piece of a much larger pattern. Another remarkable value is the ratio between the strength of electromagnetism and gravity. Gravity feels powerful in everyday life because it acts across enormous distances. Yet at the scale of individual particles, electromagnetism overwhelms it by roughly 1 followed by 36 zeros. If that ratio shifted even modestly, stars could exhaust their nuclear fuel in comparatively brief periods, or they might never ignite at all. Either outcome would prevent long-lasting cosmic environments from developing. Another constant governs the mass relationship between electrons and protons. Another influences the expansion of the universe itself through what physicists call the cosmological constant. Each value affects many others, creating an intricate network rather than a collection of isolated numbers. Adjusting one often requires adjustments elsewhere before stable matter can continue to exist. Paul Davies, a theoretical physicist known for exploring the foundations of cosmology, once described this extraordinary balance as the most compelling evidence for the existence of a designing intelligence. His statement was not presented as a religious conclusion. Instead, it expressed how profoundly the scientific community continues to wrestle with the apparent precision woven throughout nature. But perhaps the greatest challenge comes from what remains missing. No accepted theory explains why these constants possess exactly these values. They are measured, recorded, and used with remarkable success. Their origin remains beyond reach. When physicists calculate the range of mathematically possible universes, the combinations capable of producing stable atoms, enduring stars, and complex structures occupy only a tiny fraction of that enormous landscape. We therefore find ourselves living within a cosmos whose deepest numerical foundations appear astonishingly specific, while the reason those numbers exist continues to elude even our most successful theories. Picture an ocean whose surface is perfectly smooth forever. No ripples ever rise, no waves ever spread. Nothing gathers into larger patterns. A universe without cosmic inflation would have shared that kind of featureless simplicity, expanding without the tiny irregularities needed for gravity to assemble anything larger than scattered particles. The galaxies surrounding us today would never have taken shape. Cosmic inflation was proposed in 1980 by physicist Alan Guth to address several stubborn puzzles that earlier models could not resolve. His idea described an astonishingly brief episode during which space expanded at an extraordinary rate, increasing far faster than the speed at which light travels through space. The expansion itself was stretching, not matter racing through space, so this remarkable event remained consistent with modern physics. One mystery involved the horizon problem. Observations reveal that opposite sides of the observable universe share almost exactly the same temperature, differing by only about 1 part in 100,000. Those distant regions appear too far apart to have exchanged heat or information after the universe began expanding in the familiar way. Inflation offers an elegant explanation. Before that explosive stretching occurred, those regions occupied neighboring locations and had already reached nearly identical conditions. But another puzzle proved equally demanding. Measurements show that the geometry of the universe is astonishingly flat, following the familiar rules of Euclidean geometry rather than curving dramatically in either direction. For that flatness to survive until today, the earliest universe would have required an almost unimaginably precise balance, differing from perfect flatness by no more than about one part in one followed by 60 zeros. Inflation naturally drives expanding space toward that remarkable condition. The mechanism behind this tremendous expansion remains uncertain. The leading idea proposes the existence of an inflaton field, a hypothetical field filling the newborn universe with enormous stored energy. A field is simply a quantity spread throughout space that can influence how particles and forces behave. Physicists continue searching for evidence explaining what started this field, why it expanded so rapidly, and what finally caused the episode to end. When inflation stopped, that stored energy transformed into ordinary matter and radiation through a process called reheating. In simple terms, the energy fueling expansion became the ingredients from which the familiar universe eventually formed. The cosmos emerged intensely hot once again, prepared for the long sequence of events that followed. Yet inflation left behind one final gift: tiny quantum fluctuations, minute random variations in energy that naturally appear at microscopic scales, were stretched across immense distances during expansion. Those faint irregularities became the first gravitational footholds for future galaxies, stars, and planets. The European Space Agency's Planck satellite later mapped these ancient patterns within the cosmic microwave background with extraordinary precision. The measurements matched the predictions of inflation with remarkable accuracy. Even so, the deepest question remains. We understand many consequences of inflation. We still do not know why it began at all. The pace of change now became almost impossible to imagine. Every passing moment reshaped the young universe, yet the temperatures remained so immense that familiar matter still could not exist. We had reached an era filled with an intensely hot plasma, a state of matter where positively charged particles and negatively charged electrons moved freely instead of joining together as complete atoms. But expansion never stopped. As space continued growing, the temperature steadily declined. During the interval between roughly 1 second and 3 minutes after the beginning, conditions finally entered a narrow range where nuclear fusion could occur. Nuclear fusion is the process through which small atomic nuclei combine to create larger ones while releasing enormous amounts of energy. Today, we associate fusion with the hearts of stars. At this early stage, however, it unfolded across the entire universe. This remarkable episode is known as Big Bang nucleosynthesis. Nucleosynthesis simply means the creation of atomic nuclei. Protons and neutrons, the building blocks of atomic nuclei, began joining together before the universe cooled too far for those reactions to continue. Timing mattered enormously. Had expansion proceeded more rapidly or more slowly, the final mixture of elements would have looked very different. Most successful reactions produced the nuclei of hydrogen and helium. Tiny amounts of lithium and beryllium also appeared, though only in very small quantities. By the time these reactions ceased, roughly 3/4 of all ordinary matter by mass consisted of hydrogen, while about 1/4 consisted of helium. Astronomers have repeatedly confirmed this remarkable proportion by studying some of the oldest stars ever discovered, whose chemical composition still preserves evidence from those earliest moments. But the universe stopped there. Heavier elements never formed during this brief window because expansion reduced the temperature too quickly. Carbon, oxygen, iron, gold, and every other familiar heavy element required environments far denser and far hotter than the expanding cosmos could continue providing. Those elements would have to wait for another generation of cosmic engines. Billions of years later, massive stars became those engines. Within their blazing cores, nuclear fusion gradually assembled heavier elements before violent stellar explosions scattered them across space. Every carbon atom within your body was forged inside one of those ancient stars, long before the sun and its planets came into existence. The chemistry supporting life, therefore, began with these first simple nuclei and continued through countless generations of stellar evolution. After about 3 minutes, Big Bang nucleosynthesis reached its natural end. The universe still remained far too hot for electrons to settle permanently around atomic nuclei. Matter existed within an opaque plasma where charged particles scattered light in every direction, preventing it from traveling freely across space. That glowing fog endured for roughly 380,000 years, preserving within it the ingredients from which every future galaxy would eventually emerge. For hundreds of thousands of years, the universe carried light that could go nowhere. Every photon tried to move forward, only to collide almost immediately with the crowded sea of charged particles surrounding it. Progress became an endless sequence of interruptions. The cosmos glowed intensely, yet no distant horizon could ever be seen because light remained trapped within the dense plasma. But expansion continued its patient work. As space steadily grew larger, temperatures gradually declined until the universe reached another critical threshold. Roughly 380,000 years after the beginning, free electrons finally slowed enough to bind permanently with atomic nuclei. This event is known as recombination. The name simply describes electrons combining with nuclei to form complete, electrically neutral atoms. That transformation changed everything. Neutral atoms no longer scattered light as efficiently as the earlier plasma had done. Almost immediately, photons began traveling across immense distances without constant interruption. For the first time, the universe became transparent. Radiation that had spent hundreds of thousands of years trapped within the cosmic fog was suddenly free to cross the expanding universe. Those ancient photons are still traveling today. We detect them as the cosmic microwave background, the oldest light ever observed. Expansion has stretched their wavelengths over billions of years, changing what was once brilliant radiation into a faint microwave glow, arriving from every direction in the sky. It serves as a remarkably detailed snapshot of the young universe at the instant transparency first emerged. But humanity discovered this ancient signal entirely by accident. In 1965, Arno Penzias and Robert Wilson were using a sensitive radio antenna in New Jersey while investigating unwanted background noise. No matter where they pointed the instrument, the faint signal remained. They even suspected pigeon droppings inside the antenna might be responsible and carefully cleaned the equipment. The mysterious glow persisted. Only later did they realize they had detected the long-predicted afterglow of the early universe, a discovery that transformed modern cosmology. Transparency did not immediately produce a universe filled with shining stars. Instead, an extended era followed in which hydrogen and helium drifted through expanding space with no stellar light yet illuminating the cosmos. Astronomers call this interval the cosmic dark ages. Vast clouds of gas slowly gathered beneath gravity's influence while the universe waited for its first permanent beacons to appear. That waiting lasted for hundreds of millions of years. Eventually, dense regions of hydrogen and helium collapsed enough to ignite nuclear fusion, marking the beginning of cosmic dawn. The earliest generation of stars, known as population 3 stars, were probably hundreds of times more massive than the Sunday. Their lives burned with extraordinary intensity and ended quickly in powerful supernova explosions. Those violent endings scattered the first heavy elements into surrounding space, enriching the universe with ingredients that later generations of stars and planets would inherit. A long wait finally reached its turning point. Across scattered regions of the young universe, gravity slowly gathered enormous clouds of hydrogen and helium until the pressure deep within them became overwhelming. After hundreds of millions of years without a single star, the first stellar fires finally ignited. The cosmos had entered its first true age of light. Astronomers call these pioneers population 3 stars. Despite their importance, no telescope has ever observed one directly. Their existence is inferred from detailed theoretical models and from the chemical fingerprints preserved inside the oldest stars that still survive today. Like footprints left after the traveler has disappeared, those ancient chemical patterns reveal that an earlier generation once lived and died. But these stars did not appear randomly. They formed inside halos of dark matter, invisible regions containing slightly greater concentrations of mass. Those denser regions originated from the tiny fluctuations stretched across the universe during inflation. Gravity gradually drew hydrogen and helium into these natural gathering places until immense clouds collapsed under their own weight. The first stars differed dramatically from those filling today's galaxies. They were probably hundreds of times more massive than the Sun, consuming their nuclear fuel at extraordinary rates. Their interiors reached astonishing temperatures, producing intense ultraviolet radiation. Ultraviolet light carries enough energy to strip electrons away from atoms, transforming neutral gas back into electrically charged plasma. This process is called cosmic reionization. Reionization simply means neutral atoms became ionized once again after losing electrons. As more population, 3 stars ignited, expanding bubbles of ionized hydrogen spread through surrounding space until enormous regions of the universe became transparent to ultraviolet radiation. The lingering darkness that had followed recombination gradually gave way to an increasingly illuminated cosmos. But brilliance came with a price. Massive stars live far shorter lives than smaller ones because they consume their fuel with extraordinary speed. After only a few million years, many population 3 stars ended in spectacular supernova explosions. Those violent events forged and scattered heavier elements, including carbon, oxygen, nitrogen, and many others into the surrounding gas. Material that had once consisted almost entirely of hydrogen and helium became permanently enriched. That enriched gas gave birth to the next stellar generation, known as population 2 stars. Unlike their predecessors, many population 2 stars remain visible today. Astronomers find them within ancient globular clusters, dense spherical collections of old stars orbiting the Milky Way. Their chemical composition preserves valuable evidence about the explosions that came before them. Among the oldest known examples is a star designated Henry Draper Catalog 140,283, often called the Methuselah star. It is estimated to be about 13.6 billion years old, placing its formation within roughly 200 million years of the beginning. Observations like these reveal an unbroken chain stretching from the earliest expansion of the universe to the birth of stars, the creation of heavy elements, the formation of rocky worlds, and eventually the conditions that allowed observers like us to exist. Look up at any galaxy, and you might think you are seeing nearly everything that exists within it. Billions of stars shine across graceful spiral arms, glowing clouds drift between them, and bright clusters illuminate the surrounding darkness. Yet almost everything shaping that magnificent structure remains completely unseen. The visible universe is only a small fraction of the story. Ordinary matter, the familiar material making up stars, planets, oceans, living creatures, and every object you have ever touched, accounts for only about 5% of the universe's total energy content. A much larger share belongs to dark matter, contributing roughly 27%. Dark matter neither emits, absorbs, nor reflects light. Every telescope ever built has failed to observe it directly. We know it exists only because gravity continually reveals its influence. The first compelling evidence arrived during the 1970s through the work of astronomer Vera Rubin. She carefully measured how rapidly stars orbit the centers of spiral galaxies. According to ordinary gravity, stars far from the center should move much more slowly because most visible mass lies closer to the middle. But the observations refused to cooperate. The outer stars continued circling at nearly the same speed as those much closer to the galactic core. Something unseen had to be supplying additional gravity. The simplest explanation proposed that every galaxy sits inside an enormous dark matter halo. A halo is an extended spherical region surrounding the visible galaxy, filled with invisible material whose gravity binds everything together. Without that hidden mass, many galaxies would simply fly apart instead of remaining stable across billions of years. But dark matter influenced the universe long before galaxies appeared. The slight density variations inherited from inflation alone were too small to gather ordinary matter quickly enough. Dark matter began clumping first because it interacted primarily through gravity rather than with light. Those invisible concentrations acted as enormous gravitational frameworks, drawing ordinary gas into place until stars and galaxies could finally form. In that sense, the structures we observe today grew upon an unseen foundation. Physicists have spent decades searching for the particles responsible. One leading possibility is weakly interacting massive particles, hypothetical particles expected to possess substantial mass while interacting only very rarely with ordinary matter. Sensitive underground laboratories and sophisticated detectors have searched tirelessly for signs of them. None has yet produced convincing evidence. Other possibilities remain under investigation. Axions are extremely light hypothetical particles predicted by certain extensions of particle physics. Sterile neutrinos represent another proposed family of elusive particles interacting even more weakly than familiar neutrinos. Some researchers have also explored whether tiny primordial black holes formed shortly after the beginning might account for part of the missing mass. But the deepest mystery extends beyond identifying the particles themselves. Dark matter appears to exist in almost exactly the quantity needed to encourage galaxy formation without allowing gravity to overwhelm cosmic expansion too quickly. Like so many other features we have encountered, its abundance seems remarkably well balanced, while the reason for that balance continues to stand beyond the reach of present understanding. Just when it seemed gravity had written the universe's long-term story, the cosmos revealed another surprise. For much of the 20th century, astronomers expected gravity to slow cosmic expansion over time. Every galaxy should have been pulling on every other galaxy, gradually reducing the speed of their separation. The calculations appeared straightforward. The universe had different plans. In 1998, two independent teams studying distant exploding stars reached the same astonishing conclusion. These stellar explosions, known as supernovae, shine with such predictable brightness that astronomers can use them to measure immense cosmic distances. Instead of finding a slowing expansion, both groups discovered that the universe is expanding faster as time passes. The expansion itself is accelerating. But something had to be causing that acceleration. Physicists gave the unknown influence a simple name: dark energy. The term does not describe a known substance. It simply labels whatever is pushing space itself to expand ever more rapidly against the attractive pull of gravity. Despite decades of research, nobody has directly identified what dark energy truly is. Its influence dominates the universe. Ordinary matter accounts for only about 5% of the total cosmic energy budget. Dark matter contributes roughly 27%. Dark energy supplies the remaining 68%, making it the largest known component of reality. Everything we have discussed so far, every galaxy, every star, every planet, exists within the much smaller portion that does not belong to dark energy. The simplest explanation traces back to Albert Einstein. While developing the theory of general relativity, he introduced an additional mathematical term known as the cosmological constant. It represented a small energy built into empty space itself. After evidence showed the universe was expanding, Einstein reportedly regarded this addition as his greatest mistake. But the discoveries of 1998 brought the idea back into serious consideration because the cosmological constant naturally produces accelerated expansion. Yet another extraordinary problem soon emerged. Quantum field theory, our most successful framework describing the behavior of fundamental particles, predicts that empty space should possess an enormous amount of energy because of countless microscopic fluctuations. The predicted value exceeds the observed strength of dark energy by roughly 1, followed by 120 zeros. No disagreement between theory and observation in modern science approaches this scale. But the measured value also appears remarkably well balanced. If dark energy had been only slightly stronger, galaxies would never have condensed from the expanding universe because space would have stretched too rapidly. Had it been modestly weaker or even negative, gravity might eventually have reversed expansion altogether, causing the universe to collapse long before complex structures could develop. We therefore inhabit a universe whose dominant ingredient remains almost completely mysterious. Its strength appears precisely suited to permit galaxies, stars, and observers, yet no accepted theory explains why this value exists. Dark energy continues expanding the cosmos even now, while its true nature remains one of the deepest unanswered questions in all of physics. Some mysteries arise because we have not yet gathered enough evidence. Others persist because our strongest theories refuse to agree with each other. The cosmological constant problem belongs to the second kind. It stands as one of the deepest unresolved crises in theoretical physics, exposing a contradiction between the two most successful descriptions of nature that humanity has ever developed. Quantum field theory describes the behavior of fundamental particles with astonishing accuracy. It has survived countless experimental tests across many decades. According to this framework, what we call empty space is never truly empty. Every point in the vacuum contains countless quantum fluctuations, meaning tiny temporary changes in energy that constantly appear and disappear. Even perfect emptiness possesses a measurable energy density. But when physicists calculate the total energy contributed by those fluctuations, the result becomes almost impossible to accept. The predicted vacuum energy is roughly 1 followed by 120 zeros greater than the value astronomers actually observe through the expansion of the universe. No other prediction in modern science misses reality by such an enormous margin. If the theoretical value were correct, space would have expanded with overwhelming violence from the very beginning. Matter would never have gathered, no atoms would have formed, no stars would have ignited. Even the simplest interactions between particles would have been prevented by the relentless expansion of space itself. For more than half a century, generations of brilliant physicists have searched for the missing explanation. The problem has resisted every proposed solution. New mathematical approaches have appeared, attracted excitement, then revealed fresh difficulties. The contradiction remains where it began, challenging the foundations of our understanding. But one possible answer took an unusual direction. In 1987, Nobel Prize winner Steven Weinberg suggested applying the anthropic principle. This idea proposes that we observe a remarkably small cosmological constant because universes with much larger values could never produce galaxies, planets, or observers capable of asking the question. The reasoning is logically consistent, yet many physicists remain dissatisfied because it explains our observation without revealing the deeper physical mechanism that determined the value. Another hopeful path emerged through supersymmetry, a theoretical framework proposing that every known fundamental particle possesses a heavier partner particle. Those unseen partners could naturally cancel much of the vacuum energy predicted by quantum field theory. Such a balance would dramatically reduce the discrepancy. But decades of increasingly powerful experiments, including those performed at the Large Hadron Collider, have found no confirmed evidence that these partner particles exist. String theory has also offered mathematical possibilities by describing fundamental particles as tiny vibrating structures rather than point-like objects. Some versions appear capable of accommodating a small cosmological constant, but they have not produced testable predictions that observations have confirmed. So we remain in an unusual position. Our finest theories describe nature with extraordinary success across countless experiments, yet together they produce a prediction that fails by the largest known margin in all of science. The cosmological constant problem therefore endures, reminding us that the deepest structure of reality still lies beyond our present understanding. Imagine drawing the longest line you could possibly trace across the observable universe. You might expect that such an immense journey would eventually reveal a subtle bend, a gentle curve, or some unmistakable sign that space itself is warped. Yet, every increasingly precise observation continues pointing toward a remarkable conclusion. Across the greatest distances we can measure, the universe behaves as though its geometry is almost perfectly flat. This geometry depends upon the total energy density of the universe. If that density were greater than a critical value, space would curve back upon itself like the surface of a sphere. If it were smaller, space would curve outward in a shape resembling a saddle. A perfectly balanced density produces a universe whose geometry follows the familiar rules of flat space, where parallel paths remain parallel across unimaginable distances. Modern observations have tested this balance with extraordinary precision. Measurements collected by the Planck satellite indicate that the universe is flat to within roughly 0.4%. That margin is astonishingly small, when measured across the largest scales known. Every new observation has strengthened the impression that the cosmos sits extraordinarily close to the dividing line between two dramatically different destinies. But this apparent balance becomes even more astonishing when we trace the story backward toward the beginning. At the Planck epoch, the earliest interval that present physics attempts to describe, the total energy density must have matched the critical density to within roughly 1 part in 1 followed by 60 zeros. Such precision stretches beyond ordinary intuition. A slightly greater value would have caused gravity to overwhelm the expansion almost immediately, pulling everything back together within moments. A slightly smaller value would have driven expansion so rapidly that matter could never gather into stars, galaxies, or planets. Cosmic inflation offers an elegant explanation. During that extraordinary burst of expansion, any initial curvature would have been stretched across such enormous distances that space naturally became almost perfectly flat, much as the surface of an enormous sphere appears flat when viewed across a tiny region. This solution fits remarkably well with what astronomers observe throughout the universe today. But solving one mystery reveals another. Inflation itself remains an event whose underlying cause is still unknown. We can describe its mathematical behavior with impressive accuracy, and observations strongly support its consequences. Yet the deeper reason it began, unfolded, and ended as it did continues to escape explanation. So the flatness of space does not stand alone. It joins the growing collection of remarkable balances woven throughout the universe. Each precision depends upon others. Each narrows the range of possible cosmic histories. Together they form an intricate architecture in which the smallest deviation at the beginning would have reshaped everything that followed, including the galaxies above us and the atoms within you. Every object you have ever known depends upon an invisible bond hidden deep inside the heart of every atom. Long before planets formed or living cells emerged, nature established a force whose only task was to keep the building blocks of matter from tearing themselves apart. Without that force, the familiar universe would never have progressed beyond its simplest ingredients. The strong nuclear force binds protons and neutrons together inside atomic nuclei. Protons naturally repel one another because they carry the same positive electric charge. Electromagnetism tries to push them apart. Yet the strong nuclear force overwhelms that repulsion at extremely short distances, locking the nucleus together with extraordinary strength. It is roughly 100 times stronger than electromagnetism within its tiny range, creating stable atomic nuclei that can survive for billions of years. But this remarkable balance depends upon another fundamental constant whose value cannot be derived from any deeper theory. It is measured, accepted, and woven into every calculation describing the physical universe. Even a slight change would transform everything that followed. If the strong nuclear force had been merely 2% stronger, nearly all the hydrogen created during the earliest moments of cosmic history would have fused into helium before the first stars ever formed. Hydrogen would have become exceedingly rare. Water could never exist in its familiar form because its simplest ingredient would almost disappear. Long-lived stars powered by abundant hydrogen would also vanish, removing the steady energy sources that planetary systems depend upon. A change in the opposite direction proves even more destructive. If the strong nuclear force had been about 5% weaker, protons and neutrons would fail to remain bound together. Atomic nuclei beyond the simplest hydrogen nucleus could never form. Helium would not exist, carbon would never appear, oxygen would never emerge. Chemistry itself would collapse before it truly began. But the precision extends even deeper into nuclear physics. Inside stars, carbon and oxygen are created through a sequence of nuclear reactions controlled by specific resonance levels. A resonance is a preferred energy state that makes certain reactions dramatically more likely to occur. The resonance levels of carbon 12 and oxygen 16 lie within a tiny fraction of 1% of the values needed for stars to manufacture both elements in remarkable abundance. Shift those levels slightly, and one or both elements become extraordinarily scarce. This extraordinary prediction was made before it was ever observed. In 1953, astronomer Fred Hoyle reasoned that because carbon clearly exists throughout the universe, nature must contain an undiscovered resonance, making its production possible. Experimental measurements later confirmed the resonance, almost exactly where he expected to find it. The discovery deeply unsettled Hoyle. Although he remained a lifelong atheist, he described the fine-tuning of these nuclear resonances as the most astonishing example he had encountered. He later remarked that the universe appeared to be a put-up job, expressing profound scientific bewilderment rather than advancing a religious conclusion. Even today, the remarkable precision of the strong nuclear force remains another unexplained piece of the universe's extraordinary architecture. Look at your own hand for a moment, and you are witnessing a force that never rests. Every sensation, every chemical reaction, and every bond joining one atom to another depends upon the electromagnetic force. It shapes the architecture of matter at scales too small to see, yet its influence extends through every object, every living cell, and every corner of the visible universe. Unlike the strong nuclear force, which binds particles inside atomic nuclei, the electromagnetic force governs how entire atoms interact with one another. It determines whether atoms attract, repel, or share their outer electrons to form molecules. Chemistry exists because of this delicate balance. Biology follows because chemistry is possible. Every protein, every strand of deoxyribonucleic acid, every drop of water, and every grain of rock owes its structure to electromagnetic interactions. Its strength compared with gravity is astonishing. Electromagnetism is roughly 1, followed by 36 zeros times stronger than gravity when acting between individual particles. This immense difference allows atoms to maintain their structure instead of collapsing under gravitational attraction. At the scale of everyday matter, gravity becomes important only because enormous numbers of atoms gather together, while electromagnetism governs the behavior of each atom itself. But the force is not free to take any value. Its strength is determined by one of nature's most remarkable constants, the fine structure constant. This dimensionless number, approximately 1 divided by 137, measures the strength of electromagnetic interactions without depending upon any system of units. Physicists can measure it with extraordinary precision, yet they cannot explain why nature selected this particular value. If the fine structure constant were even modestly larger, electrons would be drawn more tightly around atomic nuclei. Atoms would shrink. Chemical reactions would proceed far more aggressively, making complex molecules unstable over long periods. The slow, intricate processes required for living systems could never unfold. But a smaller value creates another obstacle. Electrons would remain farther from atomic nuclei, producing larger atoms with weaker chemical bonds. Molecules essential for biology would struggle to hold together. The extraordinary molecular machinery that powers every living organism would never emerge from such fragile foundations. For more than a century, this unexplained number has captivated some of the greatest scientific minds. Physicist Richard Feynman described the fine structure constant as one of the greatest mysteries in all of physics. He remarked that every theoretical physicist should write it on the wall and spend time wondering why it possesses exactly that value. His question remains unanswered. Modern physics can measure the fine structure constant to astonishing accuracy and use it to predict countless experiments with remarkable success. But no accepted theory derives its value from deeper principles. It simply exists, shaping every chemical bond, every living cell, and every atom that allows you and the universe to recognize one another. Imagine that our universe is not the whole story, but only one page within an unimaginably vast library. Every page contains different physical laws, different constants, and different possibilities. We happen to read only the page upon which we exist. This idea, known as the multiverse, has become one of the most debated attempts to explain why the universe appears so remarkably suited for structure. The central thought is deceptively simple. If an enormous, perhaps even infinite, collection of universes exists, each one could possess different values for the fundamental constants that govern reality. Most of those universes would never develop stable atoms, long-lived stars, or galaxies. Some might collapse almost immediately. Others could expand so rapidly that matter would never gather. We find ourselves here because only a universe with compatible conditions could ever contain observers capable of asking such questions. This reasoning is known as the weak anthropic principle. In plain language, it states that any observation we make must be consistent with the conditions required for our own existence. The principle does not explain why those conditions arose. Instead, it reminds us that our viewpoint is necessarily limited to a universe where observers can emerge. But the multiverse is not a single theory. It appears naturally within several independent areas of modern physics. One example comes from eternal inflation. If the rapid expansion discussed earlier never completely ends, new regions of space continue forming endlessly. Each expanding bubble could become a separate universe with its own physical properties, creating a vast cosmic collection beyond anything we could ever travel between. Another proposal arises from string theory. This framework suggests that nature may allow an extraordinary number of stable vacuum states, meaning different underlying arrangements of empty space. Current estimates describe roughly 1 followed by 500 zeros possible configurations. Together they form what physicists call the string landscape, with each configuration corresponding to a universe governed by different physical constants. The many worlds interpretation of quantum mechanics offers yet another path toward a multiverse. According to this interpretation, every quantum event branches into multiple realities rather than producing only one outcome. Whether these branches should be regarded as separate universes remains a matter of continuing debate. But every version of the multiverse faces the same profound challenge. None has produced direct observational evidence. If other universes can never be detected, measured, or influenced, many scientists argue the idea lies outside experimental science. Others respond that a theory should not be dismissed simply because current technology cannot reach its predictions. The discussion remains deeply divided. Some physicists view the multiverse as the most promising explanation for cosmic fine-tuning. Others see it as an elegant speculation that risks stepping beyond the boundaries of testable physics. For now, The question remains open, resting at the uncertain frontier where mathematics, philosophy, and observation meet. As we descend toward the smallest scales imaginable, the familiar rules that guided everything before begin to dissolve. Matter no longer behaves like tiny solid objects following predictable paths. Instead, you enter a domain governed by quantum mechanics, the framework that describes nature at its most fundamental level. Its predictions have been confirmed countless times, yet many of its deepest implications continue to resist ordinary intuition. One experiment has come to symbolize this strange landscape more than any other. In the double slit experiment, a single particle is directed toward a barrier containing two narrow openings before reaching a detector. Repeating this process, one particle at a time, produces an interference pattern, the same pattern expected from overlapping waves. The result suggests that each particle behaves as though it somehow explores both paths simultaneously before arriving at its destination. But something remarkable happens when scientists place a detector near the slits to determine which path the particle actually takes. The interference pattern disappears. The particle begins behaving as though it traveled through only one opening. This change has been reproduced in experiment after experiment. It is not regarded as a flaw in the equipment. Instead, it appears to be a genuine feature of quantum reality itself. Physicists describe this behavior using the idea of superposition. In plain language, a particle exists in several possible states at once until an interaction forces one definite outcome. Quantum theory predicts probabilities rather than certainties, replacing the strict determinism of classical physics with carefully calculated chances. The mathematics works with astonishing accuracy. The underlying meaning remains unsettled. But quantum mechanics reaches even further. Empty space itself is not truly empty according to the theory. It contains fluctuating fields that briefly produce pairs of particles and their corresponding antiparticles before they disappear again. One consequence of these fluctuations has been confirmed through measurements known as the Casimir effect, where two closely spaced metal plates experience a tiny attractive force arising from changes in the quantum vacuum. These observations inspired physicist Lawrence Krauss to suggest that an entire universe might emerge from a quantum fluctuation. His proposal argues that our cosmos could originate from the restless activity of the quantum vacuum itself. Critics respond that a quantum vacuum is still something rather than nothing, since it depends upon pre-existing quantum fields governed by mathematical laws. The discussion therefore shifts toward an even deeper mystery rather than bringing it to an end. Another question continues to echo throughout modern physics. Why does observation appear to matter? Does an observer require a conscious mind, or does any physical interaction produce the same result? Different interpretations answer differently, and none has gained universal acceptance. You and we arrive at the same destination reached so many times before, where extraordinary experimental success stands beside profound uncertainty, reminding us that reality remains more subtle than our everyday experience suggests. Every memory you carry points in the same direction. You remember yesterday rather than tomorrow. Rivers carve valleys instead of rebuilding mountains. Stars consume their fuel without returning it. Although this forward progression feels inseparable from existence itself, the deepest equations of physics contain a surprising detail. At their most fundamental level, they generally work just as well, whether time moves forward or backward. Nothing within those equations alone demands the direction that you and we experience every moment. Our everyday world tells a different story. A glass can fall and shatter across the floor. Its scattered fragments never gather themselves into a perfect vessel again. Living bodies grow older instead of younger. Smoke spreads through the air without drifting neatly back into a candle flame. This persistent asymmetry is known as the arrow of time, and it shapes every experience from birth to the distant future. The accepted explanation begins with entropy. In simple terms, entropy measures how many different ways a system can be arranged while appearing the same overall. Highly ordered states have relatively few possible arrangements. Disordered states have vastly more. The second law of thermodynamics states that, within a closed system, entropy tends to increase over time. This statistical tendency gives the universe its unmistakable direction, even though the underlying microscopic laws remain largely time symmetric. But that explanation carries an extraordinary implication. Entropy can only increase today because it started lower yesterday. Extending that logic across cosmic history leads all the way back to the beginning itself. The earliest observable universe possessed an astonishingly low entropy, representing an exceptionally ordered condition. Modern physics describes this fact with remarkable precision, yet it does not explain why the universe began that way in the first place. Physicist Roger Penrose attempted to express just how extraordinary this initial condition appears. His calculation estimated that the probability of the universe beginning in such a low entropy state purely by chance is roughly 1 divided by 1, followed by 10, raised to the power of 123 zeros. That number exceeds ordinary imagination. It is vastly greater than the total number of atoms contained within the observable universe, leaving familiar comparisons far behind. But unlike several other cosmic mysteries, this one has no widely accepted candidate solution waiting in the wings. Inflation addresses remarkable features of the early universe, yet it does not fully account for the original low entropy itself. Neither quantum mechanics nor modern cosmology presently provides a complete explanation. The initial order simply stands as an observed fact upon which every later chapter depends. As you follow time forward, every star that forms, every galaxy that evolves, and every living mind that remembers the past instead of the future traces its history back to that astonishing beginning. The arrow of time may feel familiar because we have never known anything else. Yet its origin remains among the deepest unanswered questions in all of physics, resting beside the earliest moments of the universe with remarkable persistence. Some places in the universe challenge our understanding more completely than any laboratory ever could. Black holes are among them. They begin as predictions of elegant mathematics, yet they end where those same equations lose their ability to describe reality. As we approach one, the familiar language of space, time, and matter grows increasingly uncertain. A black hole forms when gravity becomes so overwhelming that a boundary known as the event horizon appears. Once anything crosses this boundary, no path leads back outward. Even light, the fastest messenger in the universe, cannot escape its pull. To an outside observer, the event horizon marks the final visible edge, separating the universe we can still observe from a region forever hidden from direct view. But the greatest mystery lies deeper still. According to general relativity, every black hole contains a singularity, a location where density becomes infinite and the known laws of physics cease providing meaningful answers. We encountered a similar breakdown when tracing the universe toward its earliest beginning. Once again, our most successful theories guide us almost to the destination before falling completely silent about what comes next. Astronomers spent decades searching for convincing evidence that such objects truly existed. The first widely accepted black hole candidate was Cygnus X1, identified during the early 1970s through observations of material falling toward an invisible companion. Much later, the Event Horizon Telescope combined radio observatories across Earth to produce the first image of a black hole's event horizon. Released in 2019, it revealed the enormous black hole at the center of the galaxy, Messier 87, containing roughly 6.5 billion times the mass of our Sunday. Our own galaxy holds a similar mystery. At the heart of the Milky Way rests Sagittarius A star, whose mass equals approximately 4 million suns. Its event horizon was successfully imaged in 2022, confirming decades of careful measurements and revealing another shadow cast by gravity itself. But black holes grow stranger still. In 1974, Stephen Hawking combined ideas from quantum mechanics and gravity to predict that black holes are not completely black. Instead, quantum effects near the event horizon should allow them to emit an exceedingly faint glow known as Hawking radiation. This radiation has never been directly observed because it is far too weak for present instruments, yet the prediction remains one of the most influential results in theoretical physics. Following Hawking's idea leads directly into another profound puzzle. As a black hole slowly evaporates through this radiation, what becomes of the information carried by everything that ever crossed the event horizon? Quantum mechanics insists that information cannot simply disappear. General relativity appears to permit exactly that outcome. Both theories have passed every experimental challenge placed before them. Yet here, they point toward incompatible conclusions, leaving one of the deepest unresolved conflicts in modern physics still waiting for resolution. Imagine standing beneath a sky filled with countless stars, knowing each point of light is only a tiny fraction of what truly exists. Our universe is approximately 13.8 billion years old. It contains an estimated 2 trillion galaxies, and each galaxy holds hundreds of billions of stars. Around many of those stars orbit planets, while some occupy regions where temperatures may allow liquid water to remain stable across immense spans of time. From those numbers, a simple expectation begins to emerge. Given enough worlds and enough time, life should have appeared many times. Some of those living worlds should have produced intelligence. Some intelligent species should have developed technology capable of reaching neighboring stars. But the universe answers that expectation with remarkable restraint. This contradiction became famous after physicist Enrico Fermi raised a deceptively simple question during a conversation in 1950. Where is everybody? That question evolved into what we now call the Fermi Paradox, the conflict between the enormous probability that advanced civilizations should exist and the complete absence of confirmed evidence that any have ever visited, contacted, or revealed themselves to us. The scale of the puzzle becomes even greater when we consider time. A civilization traveling well below the speed of light could still spread gradually across the Milky Way through successive generations of exploration and settlement. Models suggest such expansion could fill our galaxy within only a few million years. Against a history measured in billions of years, that interval is astonishingly brief. But our telescopes find no unmistakable signs that such a process has ever unfolded here. Decades of observation have only deepened the mystery. The search for extraterrestrial intelligence, a long-running scientific effort using powerful radio telescopes and other instruments to search for technological signals beyond Earth, has examined countless regions of the sky. Researchers have detected many intriguing phenomena. yet none has provided confirmed evidence of an extraterrestrial civilization. The cosmos continues to withhold a definitive reply. Several ideas attempt to explain this absence. One of the most influential is known as the Great Filter. This proposal suggests that somewhere along the path, from lifeless matter to galaxy spanning civilization, lies an extraordinarily difficult barrier. Perhaps very few worlds ever produce living cells. Perhaps complex organisms almost never arise. Perhaps intelligence itself is exceptionally uncommon. But another possibility remains. Ten mating, end quote. Civilizations may regularly reach technological maturity before encountering challenges they cannot survive. That uncertainty changes the meaning of our own existence. If the great filter lies deep in our past, then you and we have already crossed the rarest threshold in cosmic history. If it still waits ahead, the future becomes far less predictable. The remarkable absence surrounding us, therefore, becomes evidence in its own right. The universe has spoken through its vast stillness, even if we cannot yet understand precisely what it is telling us. After following each layer of precision woven through the universe, we eventually arrive at a crossroads. The remarkable balance of physical constants invites interpretation, yet no single path has earned universal acceptance. Instead, three serious explanations continue to shape one of the deepest conversations in modern science. Each attempts to answer the same mystery from a different direction, and each carries both strengths and unresolved difficulties. The first possibility is necessity. Under this view, the fundamental constants could never have possessed different values. They are fixed because a deeper mathematical framework demands them. Many theoretical physicists hope that an eventual theory of everything, meaning a single description uniting every known force and particle, will reveal that the universe had no alternative configuration at all. Such a discovery would transform what currently appears astonishing into something inevitable. But that hoped-for theory has not yet been found, and no existing framework has demonstrated that the observed constants must possess exactly their measured values. But another explanation approaches the mystery differently. The multiverse proposes that our universe is only one member of an immense collection, perhaps even an infinite collection of universes. Each could possess different physical constants and different laws. Most of those universes might never produce stable atoms, stars, planets, or living organisms. We naturally find ourselves in one where observers can exist because no conscious beings could appear anywhere else. This reasoning is known as the weak anthropic principle, the idea that any observation of the universe is necessarily limited by the conditions required for observers to arise. The challenge remains substantial. Other universes have never been observed, and many scientists question whether a proposal beyond direct testing belongs within experimental science. A third possibility reaches beyond physics itself. Some physicists, alongside many philosophers and theologians, have suggested that the constants were intentionally selected by an intelligence or by a process existing outside the universe. Under this view, fine-tuning reflects purpose rather than coincidence or mathematical necessity. But science depends upon explanations that can be tested through observation or experiment. A cause existing beyond the observable universe cannot presently be examined in that way, placing this proposal outside the normal methods of scientific investigation. None of these explanations escapes difficulty. Necessity depends upon a deeper theory that remains undiscovered. The multiverse offers an elegant selection effect, yet currently lacks direct observational support. Design addresses apparent purpose, but cannot be evaluated through scientific testing. Each perspective leaves important questions unanswered. For now, the most careful scientific conclusion remains surprisingly simple. We do not yet know why the fundamental constants possess the values they do. That admission reflects neither weakness nor defeat. Instead, it marks the edge of present knowledge, where evidence ends, certainty fades, and discovery still waits beyond the horizon. There comes a point where every telescope, every detector, and every signal reaches the same unavoidable limit. No matter how advanced our instruments become, there is a boundary beyond which the universe cannot yet tell us its story. That boundary does not mark the end of space itself. It marks the end of what light has been able to deliver to us since the beginning of cosmic history. Today, astronomers estimate that the observable universe forms a sphere approximately 93 billion light-years in diameter, centered on our location. You might wonder whether that makes Earth special. It does not. Every observer anywhere in the cosmos would see themselves at the center of their own observable sphere because each viewpoint is limited by the same fundamental constraint. We can receive only the light that has had enough time to reach us. But another subtle detail changes the picture. The universe is approximately 13.8 billion years old, yet the observable radius extends far beyond 13.8 billion light-years. This surprising result appears because space itself has continued expanding while light traveled across it. As ancient photons crossed the cosmos, the distances between galaxies stretched, carrying their sources ever farther away, even while the light continued its journey toward us. Beyond that cosmic horizon, the universe almost certainly continues. Galaxies may fill regions forever hidden from view. Entire clusters could exist beyond our reach. Their light will never arrive because the expansion of space prevents those distant signals from overcoming the growing separation between us. The horizon, therefore, becomes a one-way boundary for information rather than a physical wall standing at the edge of existence. How large is everything beyond it? No one knows. Current measurements suggest the entire universe is at least 250 times larger than the observable portion, while some models allow it to extend without limit. Both possibilities remain consistent with present observations. Evidence has not yet chosen between them. But infinity introduces consequences that feel almost impossible to accept. Physicist Max Tegmark explored one of those implications through straightforward mathematics. If space is truly infinite, while the number of possible arrangements of particles within any finite region remains finite, then every possible arrangement must eventually appear again. Somewhere unimaginably far away, another world could duplicate every atom surrounding you at this very moment. Another version of you could be reading these same words, sharing the same thoughts, entirely unaware of the repetition. This conclusion does not arise from imagination alone. It follows from the mathematics of infinity combined with finite physical arrangements. Whether reality truly behaves this way depends upon whether space itself is infinite, something we cannot presently determine. The observable universe therefore leaves us facing an extraordinary truth. Its horizon is not simply a distant frontier. It is the permanent boundary between what the cosmos can reveal and what may remain forever beyond our ability to know. Far beyond the lifetime of every civilization, every star, and every familiar landmark in the night sky, the universe appears to follow a remarkably consistent direction. The same expansion that has shaped every previous chapter continues without interruption, but its destination is profoundly different from its beginning. Current observations indicate that dark energy steadily drives space apart, leading toward a future known as the Big Freeze, also called heat death, where structure gradually gives way to isolation. As expansion continues, distant galaxies drift farther from one another. Their light stretches across ever growing distances until it can no longer reach us. In approximately 100 billion years, every galaxy beyond our own local group will have crossed the observable horizon. Future observers, wherever they exist, will see only their local collection of galaxies, while the greater universe disappears beyond permanent reach. The larger cosmos will remain real, yet forever inaccessible. The transformation unfolds slowly. Stars continue forming for an astonishing length of time as clouds of gas collapse under gravity. But even those reserves are finite. Roughly 100 trillion years from now, nearly all star-forming material will have been exhausted. New suns will cease to appear. Existing stars will gradually complete their lifetimes, leaving behind only their compact remains. But the darkness does not arrive all at once. White dwarfs, meaning the dense cores left behind by smaller stars, continue cooling for unimaginable ages until they become black dwarfs, objects so cold they emit virtually no light. Massive stars leave neutron stars or black holes instead. Across these immense eras, the universe becomes populated almost entirely by ancient remnants separated by immense distances. Some theories predict an even deeper transformation. Over timescales approaching 1 followed by 40 zeros years, protons, the particles forming the nuclei of ordinary matter, may slowly decay into lighter particles and radiation. This process has never been observed directly, and scientists continue searching for evidence. But if proton decay occurs, nearly every familiar form of matter eventually dissolves. Black holes survive far longer still. According to the prediction made by Stephen Hawking, quantum effects near the event horizon gradually allow black holes to lose energy through what is now called Hawking radiation. The larger the black hole, the slower this process unfolds. Some may persist for periods ranging from roughly 1 followed by 67 zeros years to 1 followed by 100 zeros years before finally evaporating into diffuse radiation. After the final black hole disappears, almost nothing remains except extremely low energy photons, lightweight particles called leptons, and an expanding sea of nearly empty space approaching absolute zero. Entropy reaches its maximum possible value, meaning energy can no longer perform useful work or assemble new structures. Complexity fades beyond recovery. The universe continues expanding, yet meaningful change becomes increasingly impossible. Time itself still passes, but its familiar story has reached its final page. Imagine the future branching into several paths instead of one. The evidence we have explored points most strongly toward heat death, yet science remains open to other possibilities that emerge from different mathematical descriptions of the cosmos. Each follows the known laws of physics as far as they can presently be extended, but each arrives at a remarkably different ending. One possibility is called the Big Crunch. If dark energy were somehow to weaken, disappear, or reverse its behavior, gravity might eventually overcome cosmic expansion. The outward motion of galaxies would gradually slow, stop, and begin moving inward. Distances that have grown for billions of years would steadily shrink. Galaxy clusters would merge more frequently. Temperatures would climb as matter became increasingly compressed. Given enough time, every structure in the universe could collapse into an extraordinarily dense state, resembling the singularity associated with the beginning of cosmic history. Whether such a collapse could truly recreate those conditions remains unknown. Another path is even more dramatic. The Big Rip begins with the opposite assumption. Instead of fading, dark energy grows stronger with time. Expansion would accelerate until gravity could no longer keep galaxies together. Later, entire galaxies would disperse. Stars would drift away from their planetary systems. Planets themselves would eventually lose their integrity. But the process would not stop there. If expansion became powerful enough, even the electromagnetic force responsible for binding atoms could be overwhelmed. Molecules would separate. Atomic nuclei would lose their structure. Matter itself would unravel. Current astronomical observations do not favor this outcome, although they have not eliminated it completely. A third proposal carries us toward an endless rhythm. The Big Bounce suggests that a collapsing universe might avoid a permanent ending altogether. Instead, the immense compression preceding a final singularity could trigger another expansion, producing a fresh cosmic beginning. In this picture, the universe repeatedly cycles through contraction and renewal across unimaginable stretches of time. It is an elegant concept, but present observations cannot confirm whether such cycles have ever occurred. Perhaps the most unsettling possibility requires neither collapse nor gradual decay. Some physicists suggest that our universe occupies what is called a false vacuum, meaning a temporary quantum state that appears stable while actually resting above a lower energy condition. A random quantum fluctuation could someday create a tiny region of this lower energy state. That region would expand outward at the speed of light, rewriting the underlying laws governing particles and forces as it passed. No signal could outrun it. No observer could witness its arrival in advance. But we do not know whether vacuum decay will ever occur. We cannot estimate its timetable with confidence. It may never happen. It may already have begun somewhere beyond our observable horizon, advancing across space without any possibility of detection before its arrival. For now, every ending remains a carefully examined possibility, while the universe continues along the only path we can presently observe. Among everything the universe has assembled across its immense history, one creation remains especially difficult to explain. After approximately 13.8 billion years of unfolding physical processes, matter arranged itself into living brains capable of reflecting upon their own existence. You and we are expressions of that remarkable transformation. Yet, awareness itself still resists complete scientific understanding. In 1995, philosopher David Chalmers gave this mystery a memorable name: the hard problem of consciousness. The question reaches beyond how the brain processes information. It asks why those physical events are accompanied by subjective experience at all. Electrical activity moves through networks of neurons. Chemical signals pass from one cell to another. But none of those descriptions explains why seeing the color red feels the way it does, why pain possesses an inner quality, or why there is any personal experience accompanying physical activity. Neuroscience has achieved extraordinary progress in identifying which regions of the brain become active during perception, memory, language, and emotion. We can observe patterns associated with recognizing a face or recalling a childhood moment. We can measure changing electrical signals with remarkable precision. But mapping activity differs from explaining experience itself. The gap remains. No accepted theory bridges it completely. But some researchers have suggested that the difficulty arises because consciousness is more fundamental than previously imagined. One proposal is called panpsychism. This idea holds that consciousness, or at least a primitive form of experience, may be a basic property of reality alongside mass or electric charge. Under this view, The building blocks of matter possess extremely simple forms of awareness that combine into the rich, conscious lives found in complex organisms. It is a fascinating possibility. It also remains deeply debated. Another controversial proposal emerged from physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their model, called orchestrated objective reduction, argues that quantum processes inside microscopic structures, known as microtubules, contribute directly to conscious experience. Microtubules are tiny support structures within neurons that help maintain their shape and internal organization. The theory proposes they perform quantum computations beyond conventional brain activity. But experimental evidence has not confirmed this picture, leaving it outside the scientific mainstream. A different approach seeks mathematical precision rather than quantum explanations. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes that consciousness corresponds to the amount of integrated information generated by a system. Integrated information describes how strongly different parts of a system work together as a unified whole instead of operating independently. According to this framework, sufficiently complex information processing may carry some degree of experience, even in systems very different from biological brains. But perhaps the deepest question reaches beyond biology altogether. Is consciousness simply one consequence of an evolving universe, or does observation itself play a more fundamental role? Physicist John Archibald Wheeler proposed the participatory anthropic principle, suggesting that observers participate in bringing aspects of reality into definite existence through quantum measurement. Whether that vision reflects nature or only one possible interpretation remains unknown. Yet it reminds us that the greatest mystery may not be the universe we observe, but the awareness through which every observation becomes meaningful. Every observation we have made about the cosmos shares one unavoidable condition. Someone must be present to make it. Before any telescope records distant light, or any equation describes reality, there must already be observers capable of asking what they are seeing. This simple fact leads to one of the most debated ideas in modern cosmology, the anthropic principle. At its most basic, the anthropic principle states that the universe we observe must be compatible with our existence because we are the ones observing it. At first glance, this may seem almost circular, but the idea carries genuine scientific meaning. It reminds us that every measurement is filtered through a profound selection effect. We can only exist during eras, within regions, and under physical conditions where observers are actually possible. That realization changes how we interpret the universe around us. We cannot expect to find ourselves in a cosmos where stars never formed, where chemistry never emerged, or where stable structures were impossible. Such universes, if they exist at all, would contain nobody capable of wondering why they appeared so inhospitable. Our perspective is inevitably shaped by the fact that we survived long enough to develop curiosity itself. But there are different versions of the anthropic principle, and they are not equally accepted. The weak anthropic principle is widely regarded as a sensible statement about observational bias. It simply recognizes that our existence influences what we are able to observe. It does not claim the universe was intended for life, or that observers shape the laws of nature. Instead, it reminds us that any conclusions we draw begin from a location where observation is possible. The strong anthropic principle goes much further. It proposes that the universe must possess properties, allowing observers to arise at some stage in its history. Whether this reflects a deep physical truth or crosses into metaphysical speculation remains intensely disputed. Many scientists regard the stronger version with caution because it appears to assign necessity where evidence has yet to do so. But anthropic reasoning has achieved one remarkable success. In 1987, physicist Steven Weinberg applied this way of thinking to the cosmological constant. He argued that if the value were much larger, cosmic expansion would prevent galaxies from forming. Without galaxies, stars, planets, and observers would never appear. Therefore, any civilization capable of measuring the cosmological constant should expect it to be small, yet not exactly zero. More than a decade later, in 1998, observations revealed that the universe was indeed expanding at an accelerating rate consistent with a small, non-zero cosmological constant. That successful prediction gave the anthropic principle new scientific credibility, but it also left many physicists deeply uncomfortable. They worry that selecting from possible universes explains less than discovering why the constants possess their values in the first place. For now, anthropic reasoning occupies an unusual place in science. It has demonstrated predictive power, yet it continues to challenge our instincts about what a satisfying explanation should ultimately be. Some questions seem natural simply because language allows us to ask them. Among the oldest is what existed before the Big Bang. We instinctively imagine every event having an earlier one, every beginning resting upon something older. But modern physics suggests that this intuition may fail at the very origin of cosmic history. According to the standard cosmological picture, time itself emerged together with the expanding universe. If time has a beginning, then the word before may have no physical meaning. Asking what happened before the Big Bang could resemble asking what lies north of the North Pole. The words form a grammatical sentence, yet they may not describe a possible location within reality. This idea was developed by Stephen Hawking and James Hartle through the no-boundary proposal. In their framework, the universe has no temporal edge where an earlier moment could exist. The apparent beginning becomes a smooth boundary rather than an abrupt starting line. But not every theoretical framework reaches the same conclusion. Loop quantum cosmology attempts to unite quantum mechanics with the structure of space and time themselves. In plain language, it treats the fabric of the universe as having an extremely fine quantum structure instead of being perfectly continuous. Within this picture, the Big Bang may have been a big bounce. A previous universe could have contracted until quantum effects prevented complete collapse, causing expansion to begin once again. Roger Penrose proposed another remarkable possibility known as conformal cyclic cosmology. In this model, the universe passes through endless successive ages called aeons. An aeon is one complete cosmic lifetime, extending from an initial expansion to an unimaginably distant future. After black holes have evaporated through Hawking radiation and only massless particles remain, Penrose argues that the geometry of this aged universe becomes mathematically equivalent to the geometry of a new beginning. One cosmic era naturally transforms into the next, without requiring an absolute first moment. But higher dimensional theories offer yet another perspective. Some versions of string theory inspired models, such as string gas cosmology and the echipyrotic scenario. These proposals suggest that our familiar universe emerged when enormous higher dimensional objects, called membranes, collided within a larger arena known as the bulk. A membrane, often shortened informally to a brane, is a multidimensional surface predicted by certain mathematical descriptions of nature. The collision would release tremendous energy, producing conditions resembling the beginning we identify as the Big Bang. Each proposal extends known physics in a different direction. Each attempts to answer one of humanity's oldest questions with careful mathematics rather than imagination alone. Yet none has received decisive observational confirmation. But there is striking agreement on one point. Every serious attempt to describe what preceded the observable beginning eventually reaches the present boundary of scientific knowledge. Beyond that frontier, mathematics becomes increasingly uncertain. Evidence disappears, and our confidence gives way to possibility. The origin of everything remains one of the few places where even our most successful theories acknowledge that they are still incomplete. There comes a point in every long investigation when the map reaches its final marked line. Beyond it, the landscape does not disappear. Our knowledge simply does. As we arrive here, you and we are no longer asking what the universe does. We are asking why there is a universe for anything to happen within it all. Physics has revealed an astonishingly precise description of reality. Its equations predict planetary motion, the birth of stars, the behavior of atoms, and the expansion of the cosmos with remarkable accuracy. They tell us how the universe changes from one moment to the next, but those same equations begin with conditions already in place. They do not explain why those initial conditions exist, why the equations themselves have the forms they do, or why mathematical relationships correspond to anything physically real. This puzzle deeply impressed physicist Eugene Wigner, who described what he called the unreasonable effectiveness of mathematics. The phrase captures a striking mystery. Mathematical ideas often begin as abstract creations inside the human mind, developed without any guarantee that nature should resemble them. Yet again and again, those same structures prove capable of describing galaxies, particles, gravity, and light with extraordinary precision. Why should this happen? Why should reality follow mathematics so faithfully? But physics, as it is currently practiced, has no equation that answers such questions. Its methods depend upon observation, measurement, prediction, and experimental testing. Asking why mathematical laws exist at all belongs to a different kind of inquiry. Science can examine the laws once they are discovered. It cannot yet explain why there are laws rather than complete disorder. More than 3 centuries ago, the German philosopher Gottfried Leibniz asked a question whose simplicity conceals enormous depth. Why is there something rather than nothing? The words remain as compelling today as they were in the early 18th century. Despite centuries of progress, no observation has settled the matter. No experiment has closed the discussion. The question continues to stand beyond the present reach of physical theory. But reaching a boundary is different from reaching defeat. Throughout this journey, science has steadily narrowed uncertainty instead of enlarging it. We now understand how delicately balanced the cosmos appears, how precisely its fundamental properties align, and how many independent discoveries converge upon the same remarkable picture. The remaining mystery has become sharper because so much surrounding uncertainty has disappeared. Perhaps that is the greatest achievement of all. Rather than pretending certainty where none exists, science identifies exactly where explanation ends and genuine mystery begins. It traces the outline of the unknown with extraordinary care. Beyond that outline, speculation may continue, philosophy may continue, and imagination may continue. Yet the equations themselves remain still, describing the universe with unmatched precision while leaving its deepest existence wonderfully and honestly unexplained. When we gather every thread of this story into a single view, an extraordinary pattern begins to emerge. Nothing we have explored stands alone. Each event depends upon countless earlier events, stretching backward across almost 14 billion years until the first moments we can meaningfully describe. You are not separate from that history. You are one of its latest chapters. Every atom within your body carries an ancient origin. The carbon forming deoxyribonucleic acid, the oxygen flowing through your blood, and the iron resting at the center of hemoglobin were all forged inside stars that lived and died long before our sun existed. Their final explosions scattered those elements across space, enriching immense clouds of gas and dust from which later generations of stars and planets would eventually emerge. We are built from material that spent billions of years traveling before becoming part of us, but that remarkable inheritance depended upon an uninterrupted sequence of events. Quantum fluctuations, tiny variations arising in the earliest universe, were stretched across space during cosmic inflation, the brief era of astonishing expansion immediately after the beginning. Matter gained a slight advantage over antimatter, allowing ordinary matter to remain after nearly complete mutual destruction. The first atomic nuclei formed, stars ignited, heavy elements accumulated. Later stars inherited those elements. Rocky worlds appeared. Chemistry grew increasingly complex. Biology followed. Awareness emerged. Every link connects directly to the next, without interruption. No step could simply be exchanged for another. Each required conditions of remarkable precision, operating over immense spans of time. Even after nearly 14 billion years of cosmic history, science has not discovered a satisfying explanation for why every necessary circumstance aligned so successfully. We can describe the chain in extraordinary detail. Explaining why the chain exists remains another matter. Our own moment occupies only a small portion of a much longer opportunity. Complex life on Earth required roughly 4 billion years to emerge after our planet formed. Meanwhile, the wider universe may continue producing suitable stars for roughly 100 trillion years before the raw material for new stellar generations is finally exhausted. Compared with that immense future, we are living surprisingly early. The cosmos is still young, but perhaps the deepest realization is also the simplest. Matter did not merely gather into stars, planets, and living cells. Eventually, somewhere within one ordinary galaxy, matter became capable of wondering about itself. Through countless natural processes, the universe produced beings able to measure its age, trace its history, and ask why any of it exists. Is that the greatest accident in the history of physics? Or have we reached a place where physics has not yet found the language to describe what happened? For now, we can only recognize the astonishing weight of the chain that carried us here, one unbroken link at a time. After everything we have followed together, from the earliest measurable instant to the largest structures scattered across the cosmos, one realization remains untouched. The universe has revealed astonishing detail without surrendering its deepest secret. You and we have traced its history with growing confidence, yet the beginning continues to stand just beyond complete explanation. Physics has uncovered an extraordinary sequence of events. The universe emerged from conditions that current theories cannot fully explain. It passed through an unimaginably delicate first, second, surviving processes that could easily have left nothing behind. Its fundamental constants settled into values that allowed matter, stars, galaxies, planets, and eventually living beings to appear. Then, over nearly 14 billion years, those same physical laws guided the formation of minds capable of reconstructing that immense story from scattered light and ancient particles. But the oldest question never disappeared. Why is there something rather than nothing? Long before telescopes, particle accelerators, or mathematical models, people looked upward and wondered why anything existed at all. Every civilization inherited that mystery. Every generation gave it new language. None has carried away a final answer. What has changed is the precision of our uncertainty. Today we can calculate how finely balanced the universe appears. We can identify where our equations succeed with astonishing accuracy and where they cease to guide us. We know which mysteries belong to observation, which belong to theory, and which remain beyond the present boundary of both. Ignorance has become sharply defined rather than vaguely imagined. But honesty demands that we stop where the evidence stops. At this moment in history, we do not know why the universe exists. We do not know why the fundamental constants possess the values we measure. We do not know whether anything preceded the beginning or whether that question itself reaches beyond meaningful language. We do not know whether fine-tuning reflects necessity, chance, selection, or an explanation still waiting to be discovered. What we do know is remarkable enough. In a universe that offered no obvious guarantee of complexity, existence unfolded anyway. Stars ignited, heavy elements accumulated, planets formed, chemistry became biology, biology became awareness. Then, upon one ordinary world circling one ordinary star, matter learned to examine its own origins and wonder how the entire chain began. Perhaps that is the most extraordinary fact we have encountered. The cosmos became capable of reflecting upon itself through beings assembled from the very atoms forged inside ancient stars. Whether that realization marks an astonishing accident or points toward a deeper truth remains unknown. Meanwhile, the universe continues its expansion. The ancient light released near the beginning continues its endless journey across space. You and we remain part of that unfolding story, carried forward by the same laws that shaped every galaxy and every atom. The question that appeared with the first moments of time has never faded. Nearly 14 billion years later, it remains beautifully, completely, and wonderfully open.